All right, so as I was saying here, just know that these were the core things that we set up in place, right? Derivative of a constant is zero. The derivative using the power rule says, hey, if your variable term is the base and you have a real number for the exponent, we can bring it down to the coefficient and then subtract one. Okay. Now keep in mind that's a real number. So I put pi up there. Just know you're going to have pi minus one as an exponent, so you can't really do anything with that. Now, moving into this problem here, though, we want to be able to multiply first so that we can get it into terms rather than two factors. So we'll have 3x squared plus 6x minus x minus 2. And then we can combine like terms. Once we get here, this is where the limit properties help us that we were talking about as far as breaking this into individual terms. Okay. So we can write this out as 3 times the derivative of this x squared plus 5 times the derivative of just x, excuse me, times the derivative of the 2. Now, what we want to get to is not having to write this step every single time. Is that clear to everyone? It's good to know that we can do this, but it only is true because we went from something that was in a factored form to terms. Once we get to terms, this multiplication is different because this is what we call, again, a constant multiple. Right? We were just multiplying by 3. So that's why we can treat that multiplication different. But using the power rule on this first one, we'll get 3 times 2x. What did we say the derivative of just x was, though? Right, just 1 there. So this would be plus 5 times 1 minus 0. So just cleaning that up a bit, we just get 6x plus 5. Now, with that set in place, right, we can move into this and say, hey, what we hope to be able to do is kind of get away from these extra steps and see the connection that we have here. That's what we want to work towards. Now, as you need those other steps, make sure you fill in with helping you see where it's coming from. But make sure you see here that, hey, I know I'm going to use a power rule here. So when I bring this 2 down, I need to multiply it with a 3 because it was already there. Okay, and then 2 minus 1 will give us just 1. Any linear terms you have in a polynomial, hey, that's going to get rid of the variable right there because derivative of x is 1. So that's why we'll just put 5. Derivative of any constant term is 0, so I don't want to put anything. All right. Now, as you start skipping steps, so always double check your work because things that would be easy to do is accidentally forget to get rid of the constant term. Like going too fast and you keep a minus 2 when you weren't supposed to. Just little things like that can happen. But no, that's what we're going to be working towards as we go through this. Okay. Now, here we had to multiply to get to that point. What do you think we need to do here?
To x to the power half.
Right, so those are rationals, exponents. That's exactly what we want to do. So understand with radicals, we want to convert it to rational exponents. Okay, so you'll see with this second one here, we'll say, hey, let's do the derivative of x to the 1/2 minus x to the 2/3. With that said, make sure you remember that's a power over the root. So since it was x squared, that's why I have it as 2/3 rather than 1/3. The good news is once you do that, when we go take the derivative, we're going to treat just like we did x squared. We can go through here and say, hey, I'm going to do the derivative of each of these separately now. That's going to be the square root here. Since there was no exponent on x, that's why I'm putting the 1 at the top. And then whenever you have a square root, the root is understood 2. We don't write the two, but it's understood that, okay? That's the main one that you just kind of have to, hey, square root exponent 1/2. That's the one you definitely want to make sure to remember. Like, nice thing about cube roots, we see the 3, right? With those in place, though, make sure you see here when we do subtraction, sometimes we're going to get negative exponents. That can happen.
Itself is the root, right?
The radical, yeah. This one had the 1/2 because it was a square root. This one had the 1/3 because it was a cube root. Just make sure you see this squared came from that. The fact that it happened to have an exponent. That's not always going to happen, right? But that one did. Make sure you see here, though, 1/2 minus 1 is negative 1/2. 2/3 minus 1 is where the negative 1/3 is coming from. When you start dealing with irrational exponents, when we subtract, hey, guess what? I'm going to have a negative after I do that at some point. Now, the other thing I would say here is always read the directions on the work is concerned. We have the derivative there, right? The only thing that can change here is if something comes in and talks about wanting to simplify something. All right. So the only thing I could say that we could do to simplify here, it'd be like, hey, 1 over the 2 times the square root of x minus 2 over 3 times the cube root of x. But at that point, that's just a different way of writing it. Okay. Make sure you see, first and foremost, I move the variables into the denominator, right? Remembering that, hey, we don't see it all the time, but anytime you have a negative exponent, that just means move it to the denominator, okay? The square root gets connected back to the 1/2, the cube root gets connected back to the 1/3. For the most part, though, if it's just asking you to find the derivative, I'm pretty confident saying that we could stop here. The tough part is, hey, this is probably easier to put in the calculator if you have to go a step further. So there are times where the radical notation is beneficial. Any questions with that one clear for somebody? Now that's one area where, hey, knowing the power rule for derivatives will help us a lot. Okay, just kind of point out to you real quick. If we were to look at this from the perspective of the notation of like, hey, f of x equals the square root of x, f prime of x then equals the limit as h approaches 0 of f of x plus h minus f of x. So we use the limit definition. This gets tedious. All right, I think I did that one in class or something similar to it a while back. Right, but understand this is where we have to go in and say, hey, I have to do some rationalization to be able to do this. This isn't something we want to have to do every time. So recognizing that, hey, I can change it to a rational exponent helps you a lot in the process of getting to a derivative. Everyone follow me on that? If you look back in the notes, though, this is where we have to actually go in and multiply by this on top and bottom. And once you do some simplification, it works out where the h's can divide out, okay? Well, make sure you see here, it's like, hey, I'd rather just go straight 2 through the power, okay? Any questions, though, with these two?
The last, how the x has the minus. Half.
Talking about here?
Yeah.
So what does the power rule tell us to do? So that was its exponent, right? So the power rule says take the exponent and make it a coefficient by multiplying. But then we need to take the exponent. Once we go here, we're subtracting 1. So this is 1/2 minus 1, where that comes from.
Okay.
And then 2/3 minus 1 is why it's negative 1/3. All right. Now, the other ones that we looked at, the second one here that I had set up as far as the grouping is concerned was make sure we're comfortable with what I call Leibniz notation, right? I understand we're still trying to find a derivative, but what you'll see sometimes it's better to write it in a different way depending on what you're trying to get to. One of the things that you'll see here, this is going to allow us to look at it from different perspectives. One of the things that we will run into going into this is what we call implicit differentiation. So we might have y squared equals this at some point, and we need to know how to handle it. Well, limited notation helps us with that, okay? That's not what we're doing here right now. But what I hope that you see to help with our differentiation, you can write things differently. So here I brought something that has division in it, but as we just talked about negative exponents, we can rewrite this to help ourselves out. So make sure you see here, I just brought in the derivative notation. Whatever I do to one side, I do to the other, but make sure you see I changed the negative 2 over x to the fifth. I just used it as x to the negative fifth. So we don't have a fraction any longer. Over here, hey, that's the same thing as what we're trying to find. So dy dx, we don't need to do anything, just write it as dy dx. You could have wrote that immediately. Okay, I'm just making sure to show that with this step here, we're differentiating both sides. Over here, though, now we can use the power rule. Okay. I'm going to leave the negative 2 alone, but what do I need to multiply by now? Does everyone agree with that? Negative 5? That's my current exponent. Now be careful here, though. When I go to my exponent now, it's negative 5 minus 1, right? So what does that become? Negative 6, right? Good. When we start dealing with those negatives, it does get kind of messy because, hey, I got to remember I'm subtracting 1 from it. Make sure you see, though, when we do the derivative, it goes from a negative to a positive because of the multiplication there for the coefficient. Now, as we talked about that very first one we did where, hey, we had multiplication. If I multiply that out, I get to terms, I can move forward. Here, I had a fraction. That doesn't really follow the power rule, but by making a negative exponent, now I can move forward. Questions with that one? Any concern, though, with that negative exponent and then using the power rule? All right, now, one thing though, as I said, be comfortable using both the function notation as well as a Leibniz notation, okay? Know that sometimes they're interchangeable, sometimes they're not, just depending on what you're working with, because here, when you're dealing with function notation, we know that when I plug an x value in here, how many numbers am I gonna get back? You plug in 0 right now, what would it equal? It'd be 0. If I plug in 1, how many values will I get back after I simplify? A single number, right? Does everyone understand that? Function notation means that, hey, for each input, I will get exactly 1 output, right? There are 3 terms. I don't disagree with that, but then you would have to go do the subtraction addition, and it'll give you a single number back. When I start dealing with this notation there, that allows us to then branch off and say, hey, sometimes we don't necessarily need a function to work with, right? So that's why I mentioned I could give you something like y squared equals the negative 2x over fifth. So that's why it's good to have both of them in place, because it's not always going to be a function we're working with. Now, as far as this next one is concerned, though, it's giving me a function that says identify the slope of the tangent line at x equal to 3. All right. Well, to get slopes of tangent lines, if I have a function, this is where we need to say, hey, I also now need the derivative of that. And so when I write out the function notation f prime of x, what I'm saying is I want to find the derivative of that function that we started with. That doesn't look exactly like the very first problem we did, but understand it's terms, so I can definitely do this now, just going straight through it. If you need to write it out, please make sure you do. All right. The first thing we're going to focus on, though, what is the derivative of x to the fifth? All right, so we're bringing that 5 out front as a coefficient, right? And it's x. Do we need an exponent? If it was x to the fifth, it should become what now? So fourth, right, subtract one there. Everyone's good with that? So since we're moving from the original function now to the derivative, make sure you see here how we write things is very important. I'm no longer working with the original function. I'm now working with the derivative of that. So that's why this notation is very important. So I started with x to the fifth, but by the power rule, I bring that 5 down and I subtract 1. Well, that doesn't necessarily completely change over here. Now I'm going to put minus what? Minus 3. What's going to happen to that 3, though, as we work with the second term? What we have a coefficient of 3, right? What is the exponent there? 3, right? So I'm going to do negative 3 times 3. X with what exponent? X squared, right? If you need to write that, that's fine. Nothing's wrong with that, okay? That's why I was saying, like, if that's going to help you see what's going on, please put it. But know at the same time, as you get comfortable with that, that's an extra step that, hey, I can just kind of make sure I visually go through each term as well, okay? I know I did that last Wednesday, especially just to make sure to connect, hey, those limit properties are going to carry over. Now, as far as that concerned, why am I putting just plus 7 at the end? When we take the derivative of that, right, the derivative of x is going to give us 1. So, hey, that's 1 times 7, which is 7. Now, keep in mind also, as you deal with this, you didn't have to put 3 times 3 here. You could have just recognized, like, hey, that's just going to become minus 9. 3 times 3, yeah, I can just put minus 9. If you need the extra step, though, please put the extra step. It's better to put the extra step to make sure you're comfortable with something than skip through stuff. Now, do I need to do anything else? So I have the derivative, right? But what did the problem ask us to do with it? That's the next question. Now I need the slope. How do I get the slope of that tangent line? Plug 3 in where? And it's f prime of x. This is going to be where you have to say, hey, the whole point of getting this was to find a rate of change, right? So if I plug in f prime of 3, I'll find the slope of the tangent line right there at the value of 3. Okay. Now I'm going to use my method that I like, but plug it in a calculator, however you're comfortable with. Are we in agreement here with something with others? There's no, like, if you, hopefully you see here, if you choose to do a synthetic division, make sure you put your zeros. That would be definitely something that messes it up. Putting this in a calculator, I feel just as easy to do, okay? That'd be one thing I encourage you is practice making sure you could put an entire thing into your calculator. All right, if you ever want to learn how to put it into where you can try different values quickly, come see me during my office hours. That's one thing we can look at. I might have to mess around with it with a second, but there's a way to do that on those where you can put a function in there. And then if you're careful, you keep redoing a function with whatever number you want to plug in. Okay. Now, this particular problem, though, we just found that 331 represents what? The slope of that tangent line at that value. Is that clear to everyone? It's the instantaneous rate of change when x is 3. Any questions with that? Or concerns? Or we go with the derivative? That's definitely the important part here. Well, let's look at something else then. What if I gave us this application problem? Talking about average price of baseball tickets. If you don't want to have to write the whole thing down, feel free to take a picture. But make sure you see here, though, that this is saying that, hey, if we look at the average price of tickets from 1990 moving forward, we can use this function to kind of model the change in ticket price. All right. Please keep in mind that as with stuff like this is where we're getting into stuff that is a model. All right. If you start looking at ticket prices throughout the years, we're not saying that this is going to be a perfect representation of any year we looked at that. And in fact, I don't even know if they really went in and looked at this from a actual perspective or made it up. That would be the interesting thing to look at. Okay. Now, what you'll find here is if we look at all those years and data points, hey, this function probably can be close to modeling that. Okay. With that said, make sure you see here, they call it P of X because that's going to represent the average price in whatever year I put. But be careful, whenever I pick an X value, what year do we have to keep in mind? So 1990. So if I say X equals 5, what year are we referring to? What was that? 1995. Is that clear to everyone? It's definitely important to understand. We're going to be able to plug in just some whole values, right? We can use any whole number here. 0, 1, 2, 3, 4, and so on. But make sure you connect it back to say, hey, I got to do 1990 plus this to know the year that it's referring to. Now, what they want me to do now is 3 different things. The first thing is, let's go find dp dx. What's another way to write that? E prime of x, okay? So don't let the notation and what they put in the textbook or something change you on there. Just make sure you remember that, hey, that you're trying to ask me to find the derivative of my function. With that in mind, whether you write it as dp dx or p prime of x, remember that means we want to take the derivative of the function we were given to start with. So as we do this derivative here, going to our first terms, it's we're already in terms, right? We just go one at a time. What's the derivative of 9.41? We all go with y at 0. What's the derivative then of the negative 0.19x? It's a nice linear term, right? Just x on it. So, hey, I keep the coefficient. Any concerns with that one? What about this last term? What's different about it? All right. So we got to do that multiplication, right? What did you get from that multiplication? We did 0.09 times 2.
0.
Well, an agreement there? Make sure you see here what we did was the power rule, 0.09 times 2 times x to the first. We don't need to keep that 1 as an exponent though. That's where it's coming from. Now, that's just the first part, right? At that, we can say, hey, I found what they wanted in A. Now, with that said, keep in mind, what did P of X itself stand for? The average price. What does P prime of X stand for? The rate of change of the average ticket price. Okay, so always keep that in mind, because what's going to happen is when you start getting to some of these problems, and they'll be like this on the test, you need to make sure to read what it's wanting you to actually look for. Okay. When we go to part B, that's a good example here. It wants me to then go find the average price. So which function should I plug into?
Yes.
We plug into the original function and the derivative function to find the average price. The original. Now, with that said, for 2010, since we're looking at that one, for 2010, what is our X value? Does everyone understand why it's 20? Any concerns there? Is everyone good with where we got our derivative from? This would be a good example of making sure you have a calculator, right, that you can go plug this into. So let's make sure we do that. So if we look at P of 20, I got 41.61. What did I put with that?
The average ticket price.
All right, but as everyone see how I snuck in the dollar sign there when I wrote that to make sure to remind myself, hey, that's the average ticket price. Okay, so we look at all the ticket prices that during 2010's Major League Baseball season, the average price was $41.61. All right, now what changes though when we go to the next one? What was that? My derivative function, right? We got to go use P prime of X for this one. So make sure you see the difference between these two. This one says, what is the rate of change of the average ticket price in 2010? So really what we're trying to say, hey, in 2010, as we look at 2010 and the years before or after, was the average price going down or was it going up? Okay. The average price was 41.61, right? But when we look around the other years, let's see what it says. Well, P prime of 20, we now got to use our other function, right? This time we got $3.41. Okay. So what were the average ticket prices doing in 2010? Were they increasing or decreasing? Increasing, right? Does everyone see it? Because we had a positive number. Now, was it a lot? Not necessarily. It was a little less than 10% of the average price that's increasing by. Okay. With that said, how can we use that to say predict the ticket price in 2011? Did everyone hear that though? If we want to kind of try to predict what would happen and say, what might the ticket prices be in 2011? Like if you're trying to budget for going to games the next season, right? Know that you have the average from 2010, right? Well, you could add our derivative to it. That'll give us a good approximation. That doesn't mean it's going to represent that perfectly. But if we go back to our function and I calculate 21, I get 45.11. Okay, that's just me plugging it into the thing to get the average price. That's what our model says. Well, if you do the 41.61 plus 3.41, you get 45.02. It's pretty close to what our model gave us and what we would predict. Does everyone follow me on that? Are we good though, as far as seeing, making sure we're reading to see when to use the original function versus the derivative function? That's definitely an important part here. I think I probably said rate of change a lot. I get tired of hearing that, but that's definitely one of the things that we want to make sure we're pointing back to, okay? Any questions with this one? All right. With that said, we got a couple minutes left, so I'm gonna do this one situation here. This is gonna be more for introductory purposes, but as we deal with this, those other functions we worked with were nice because we got them into those terms and we can go individually by terms to be able to differentiate. That's not always going to be possible. There's going to be times where you have multiplication and you have to find a way to work around the multiplication. Okay. For example of one that we can't really distribute, what if I gave us 2x times the square root of x plus 1? We can't really distribute into a square root, so we have to have a way to deal with this. Okay. With that said, this is where what we call the product rule comes into play. So you'll see here, I gave it out of the textbook for us. So anytime you have a function that is made up of two functions multiplied together, this would be a good example. Both of those themselves are lines, right? We call them linear functions. They're being multiplied together. You can differentiate it using the product rule. What you'll see here, though, the product rule says keep your multiplication, but it'll be the first function times the derivative of the second function plus, and then alternate. The second function times the derivative of the first function. So what you're seeing here is instead of getting one term when I'm done, I'm going to end up getting two terms where I alternate, hey, one function times the derivative and then the other function times the other derivative. Okay. Now, with that said, what problem did I pick for my first example? Where did I get this from? The beginning one, the one that we talked about how, hey, I can distribute that out and then do the derivative, right? So make sure you see here as we go to do this one, we better get 6x plus 5. Otherwise, something's wrong. With that said, make sure you see here the way that we're going to approach this is say, hey, f of x equals 3x plus 1, and then g of x will equal x plus 2. All right, so I'm going to treat them as two separate functions. With that in place, I'm going to have to take the derivative of both of these. Does everyone understand that? So let's go ahead and do that now just so we can have it in place. And all we have to do then is take what we have and put it where it belongs to help with the process. So what you'll see here is, hey, if I differentiate this, what should we get? So do we all agree with 3 here? Derivative of 1 is 0, right? So that's gone. That's a linear term, so it's just 3. Now remember, we should expect 3 because that was a line, right? The slope of a line is mx plus b, right? We get it from m anyways. What's the derivative of x plus 2 then? Just 1, right? So it'll work out nicely. The key is now is to remember, hey, it's going to be first times the derivative of the second plus the second times the derivative of the first. So whenever I go through the product rule, that's what I'm going to use to help remember. Hey, first times the derivative of the second plus second times the derivative of the first. So now that I have all that in place, I can go down here and say, hey, the derivative that we're looking for is found by taking that first factor and multiplying it with the derivative of the second factor. So make sure you see here, g of x, that second factor derivative, we got just 1. So 3x minus 1 times 1. Then we're going to say plus. We're going to do the x plus 2 times the 3. We have the derivative now. Okay, but what do we need to do to it? And we'll do our simplifying skills, right? This would be just a situation, have the derivative, right? Make sure you understand that at this point you have the derivative. We need to simplify it though when we can. So hopefully what you see here though, that first one works out nice. Don't change the sign though. Okay, be careful with the second one though, with your distribution to get to 3x plus 6. All right, I'm keeping a plus sign in between though, because that's what the product rule gives us. So that when I go through to this next step, I get 6x plus 5 when I combine like terms. Is that what I should have gotten? Everyone see how that worked out nicely for us? Now, as far as the amount of work is concerned, you can choose between what we did earlier or this. I feel both of them kind of what when you're dealing in this situation. But keep in mind, as I mentioned, there's going to be problems where we do need this to move forward. Okay. Now, my plan with that then said is tomorrow to come in and let's continue working with this, making sure we're comfortable with differentiating things as far as polynomials or anything I can use limit properties with to break down. But know that, hey, now we have a way to deal with multiplication. If we talk about multiplication, guess what else we're gonna have to talk about? Division, okay? Division. Now, the good news is thinking like this will help you get away from division to multiplication. So if you ever get stuck, just know that you can use negative exponents to create the product. So as long as you have the product rule, we can move forward, but that's definitely going to be our next step. Okay. Any questions, concerns though, as we finish up today? All right, well, if you don't have any questions or concerns, have a good day. If you came in after I took roll, make sure you see me so I can update the attendance. If you're all good, have a good day and I'll see y'all on Wednesday. And I'll do my best, y'all, to get the test graded as quickly as possible, but I can't guarantee a day because every single one of my classes took a test this past.
Okay.